Hello everyone, this is Jim Chastain with EasyPower. Welcome to the EasyPower Tuesday refresher session. Today we're going to tackle the topic of ground fault coordination in EasyPower and spend a little bit of time trying to cover some common mistakes that folks run into when they're trying to tackle ground coordination. Welcome all. Here's kind of our agenda. Talk a little bit about the pros and cons of grounding systems historically, and then jumping into, as I say, trying to illustrate some common mistakes, and which is always a little challenging when you're trying to do it live in front of an audience. So we'll see how forgiving you can be. One of the things you'll find is that there's multiple options in attacking the grounding system. And while this is not an exhaustive discussion by any means on the topic, primarily we're trying to focus on the use of the tools in the coordination process. And I really would refer you to other sources as far as recommendations on the types of grounding for your particular system. With that in mind, let's kind of do our poll questions. First question is, for grounding projects, what type of devices do you primarily depend on or use? So let's see what kind of responses we get from the audience. Obviously, there's no combination or right or wrong answer, but we do appreciate your feedback. And hopefully, we'll be able to deal with displays or examples that answer some of the questions. Now today, I didn't mention today, we may be time limited. So by all means, enter questions as we go along. If we can't get to them, we'll answer everything via email after the session. It looks like we have a quorum on our poll. It looks like kind of a common distribution of the concerns that folks have when talking about this. And so the next question is, which types of devices are most difficult for you as far as your coordination efforts? Now I notice fuses is coming up often in the discussion. I'll try to illustrate that. I didn't have an example picked out, but we'll make a note of talking about that briefly. It looks like we have a quorum on the topic, and here's how folks have weighed in on this. Looks like a fairly common distribution. And again, I may have to go back and change my example list, but let's deal with it. Thank you for participating, and again, thanking you for joining us today. Okay, historically, the choices to do grounding or ungrounding have kind of gone back and forth a little bit like a pendulum, and so what might have been the choice today or the recommendations today may not be what was common wisdom or common knowledge 20 years ago. But historically, hard grounded systems improve the safety as far as ground fault and preventing electroshock. And they were easy to detect the ground because when you had a fault, everything stopped, or at least the parts that had protective devices on them stopped. The con, or the downside, is that currents could be relatively high, and in some cases could actually initiate an arcing fault. And where ground faults are probably the most common types of faults in the electrical systems area, they are a common initiator of arcing faults. In addition, when you have multiple devices in a hard grounded system, they probably need coordination, and it's challenging, especially if you're using multi-case circuit breakers, because in some cases on the downstream faults or downstream loads, a fault will be sensed by some phase over current protection. And as we kind of mentioned, when you did have a ground fault, it usually meant you had at least a partial shutdown, depending upon how granular your fault protection scheme is. Now, ungrounded systems, again, at one time were fairly popular because it does limit system outage by letting systems run with some amount of fault current or ground current in the system. And the anticipation was it allows us to run even somewhat limited, on a limited basis if necessary, and be able to repair stuff during a system shutdown. The downside of an ungrounded system was sometimes it was difficult to locate a current fault, especially if you had multiple faults in the system. And since they were caused by insulation failures, they could be widely distributed and consequently even more difficult to find if you're under the time constraints of a shutdown period. Today, when we have an ungrounded system, frequently it involves some sort of monitoring so you can kind of do a health check on the system from time to time. In the early 80s, so there's kind of a segregation here between resistance grounding and high resistance grounding. Resistance grounding is usually referred to where we have a fixed resistor in the system that limits the current and allows me to monitor the current through that particular leg or ground point. Frequently, that would be the ground on the transformer itself. And then in the early 80s, there evolved the process of high resistance grounding, which involved some sort of reactance, which allowed the ability to limit the ground current and consequently the electroshock, and at the same time allows the system to stay up with multiple ground faults with some monitoring involved. Again, it was somewhat difficult to locate the ground faults if you didn't have the monitoring system widely distributed, and at the same time it does require some coordination for best results. Generally, in a relay and breaker nomenclature, the ground time over current and neutral time over current are optional, available options. Instantaneous overcurrent, again, can be used as a last line of defense when you know what the fault currents in the low voltage section can be. And then it's necessary to select CTs that are in anticipation of what that ground current monitoring needs to be so that you're not necessarily overstressing an overcurrent CT, or if you're using a zero sequence detection relay. Now the trade-offs, there's really not any hard and fast rules on ground fault coordination or protection other than recommendations by the NEC that ground fault protection in low voltage systems required on 1,000 amps or greater, that the max setting for ground fault protection or tripping is 1,200 amps and the max delay above 3,000 is 1 second. And so it really comes down to the risk-reward trade-off the facility is willing to make in terms of the loss of service versus the cost of implementing ground fault protection. And if we're talking about just add-on features or sometimes features that are available in existing protective devices, it's relatively low compared to what we would lose if we lost a bigger section of the plant due to lack of ground fault protection. So in a typical resistor grounded system, the first level of protection would be the 50G, and in this case the CT ratio is 50 to 1 that we're showing here on the BH2, and the pickup set for 5 amps. On the second level of protection, 51N is fairly common. And again, we're shooting for about a 25% pickup, and make sure that your CT is set above the relay, the trip setting, so that you're not maxing out on a maximum fault. And likewise, the last level is a 51G, which is set above the 51N recommendations as far as the set points. Now, I'm going to go through some of these examples, and like I say, it's always a little bit dicey trying to do this live, but hopefully it'll be somewhat forgiving, and I end up painting myself into a corner. And so these are the areas that we need to focus on when we're coordinating these particular functions. Now, in a solid grounded system, where the ground fault protection pickup is greater than or less than 1200 amps, we would probably depend upon the breaker, ground protection, and when we're trying to coordinate with the fuse, we set the I²T setting to N specifically for fuse coordination. And when we look at the time current characteristic curves, what we're looking for is, in this case, we have two ground fault breakers with ground fault protection built in. This is the instantaneous setting for ground fault in a breaker, and we've got it set to trip at a level of current that exceeds, it looks like, about 10 amps at a minimum, and then is protected by an upstream ground fault breaker, which is more likely the main. And then at the same time, we're also isolating or protecting one of the other loads with a fuse, and we've got the N setting, the corner clipped off of the main breaker, the main ground fault breaker, to allow coordination between the fuse and the main breaker. Okay, so as I mentioned, we're going to try to illustrate some of these. It turns out there's an example in EasyPower, the sample folder, Protection 1, and as I indicated in the write-up for this webinar, frequently there's questions that come in on the same topic, and so we're going to try to touch on those, and those kind of fall into the category of common errors. And so the file I'm using is in the EasyPower one-line folder under the sample folder, and it's called Protection 1. And if you have the tools, because there are a number of, if you will, mistakes or error settings in this particular sample, it's something that's worth playing on or tackling. So we're looking at here is the one-line diagram, and we've got multiple levels of ground protection, both on the transformer and on the main feeders. And this is a relatively high voltage system. First thing I like to start with is going into the short circuit focus, looking at the half cycle current, and fault in the bus, or fault in all the buses. And what we see here is the current that we would expect, the maximum current for a three-phase fault. Well, to look at the fault current, we're really talking about a line to ground or a single line or a dual line to ground. So if we select, and I'm up here on the second row, the type of fault to be a line to ground, we see the current that would be converging on each bus. And if we fall to just the main switchgear bus by itself, what this tells us is a number of valuable pieces of data. First of all, the worst case fault that we would see on the downstream side of the transformer is 379 amps. So we can use that as the maximum point for our ground fault protection, knowing that it will never exceed, or at least to scale our CTs and our current, knowing it will never exceed that particular number on a through fault, or on a fault, period. Now on a through fault, the maximum current that we'll see on the primary side is 26 amps. And so when we're talking about fault protection for R3 up here, we can actually use an instantaneous setting because this will be the maximum current on a through fault. Anything beyond that, we could assume to be an internal fault or a fault upstream of the transformer. So let's see if we can't tackle some of this. If I go back to database edit and I'm looking at R3, a couple things I want to check. And when I mention errors, these are kind of common errors. So again, this is a 51N. If I look at my setup, I've got a CT that's CT3, and I've properly selected that as far as my my function on the breaker, the relay. I have this equipped to trip BH1, so I need to indicate that on my setup. So it's going to be a high voltage breaker BH1. And then finally, I want to look at my device function, and I see that I've set here device function 5150, when in fact it's going to be a 51N. So let's kind of go to there. And as we select that, we should be in good shape to go to settings. Now I want to double check to make sure my CT ratio is matching what's being used on the one line. This is a single function device. We're looking for a maximum setting of 26 amps. So I have this on the kind of the second to the lowest range, and I think 26 amps is going to be probably close to 0.6 or 0.8. So if we set this to trip at 32 amps with a relatively slow trip or quick trip time, we should be in pretty good shape. So let's close this. Let's go to coordination, select the breaker, or excuse me, the relay, CT, the breaker, the transformer, and the downstream bus. Now as I plot the TCCs, one of the common complaints or suggestions that come up is, first of all, we're looking at both phase and ground coordination. So I just want to look at the ground coordination. And frequently, people will say, Jim, I get my relay set up and I go to the ground display and nothing shows. Well, the first and the most common mistake here is that we don't have a ground fault indicated. So if I go to a single line to ground, in fact, I do see my relay curve. And if I look at where it's set, I'm showing, if I look down here at the bottom tab, I'm showing it's set to pick up at 380 some odd amps. Well, Jim, I thought we were talking about 26 amps. Where does that? Well, if you look down at my scale, I have this set up for the 13.8 voltage reference, and we actually have this relay set up on the primary side, which is 115 volts, 115,000 volts. If I right click on the plot, TCC plot, and go to the scale setting, I can change the reference voltage to 115K. And let's go ahead and use a current scale of 1. And now if I look at the pickup setting for and this will indicate up here as well. If I look at the pickup setting, I see it's set for 32 amps. And that particular, if I look at a tick mark, I want to set a 30 cycle for 36 amps. So this is where it's going to trip if this bus faults slightly above that point. And so my curve disappears, which is a good sign because now it's meant the device is tripped. If I don't select any breaker, then it brings it back and gives me some kind of confidence it's going to trip at 32 amps. So let's say we're going to leave that as it is. Let's go to the next device. So I'm not going to, yeah, I will save this as part of the system and go back to database edit, save the changes that I've set up in my R3. Now, another thing I want to look at is for these relays on the ground connection. I can see I have a resistor grounded transformer, but I don't show any value for the resistor itself. I see a CT and actually two CTs. If I go into the transformer winding impedance, I can see that I'm indicating there's a resistor in place, but I haven't calculated the value. And so by doing calculation or click the calculate button, I get the amp class of 400 indicated. And so now I see the value show up. So it gives me an indication of what I need to scale my CTs for. All right, so I'm going to work on R4, which is this puppy here. And if I go into the settings, I got a couple things going on. First of all, let's say if this fails, I want to open up the breaker CT2. Again, this is something that may differ on your particular indication. You may want to open up BH1, but in my case, I'm going to do BH2 just for ease of discussion. So I'm going to select high voltage breaker BH2. Now here's something that jumps out at me. For both the ground and the phase over current, this is a multifunction relay. In one case, it's looking at the current drawn from in the phases of the transformer, and then the second function is at the neutral current on the transformer with a different CT. But in my setup, I've got the same CT number, so I need to correct that as far as what I'm looking at. And I'm going to go to settings. Now that I'm happy with this, I want to look at the function 2. Now here, I think we were looking at a maximum current. It seems like I don't remember what the maximum current was. I'm going to save this, go back to short circuit, go to a current, fault the current, look at a single line to ground. So 380 amps, if we had a fault to ground, 380 amps would be the maximum current. I'd be sensing this with the 400 amp CT or 400 amp resistor. So I can go back now into my database and set this up for function 2. And let's set it up for, so I've got a 0 to 999. I think I'm going to be somewhere around 9. I can hunt and peck a little bit, but let's see what this gives me. So if I'm shooting for 389-ish, I think it's going to be 9.5. All right, we're using fixed time. We could use inverse or not. Let's see where the fixed time puts us. Now when we go into coordination, we're going to select transformer, the relay, the CT, and the downstream bus. Plot the same kind of thing here. We just want to display the ground. We want to display a single line to ground, and we want to fault all the buses. And by opening up this, we can change the appearance on the breaker, sometimes the relay, sometimes it's easier to identify if we put more weight on the plot. And what we're looking at is this current right there, which gives me, let's see if I got this right. I'm on the 13/8 scale times 10. There's my max 399 on R4-2. So anything above that will be a fault. And if I fault this bus, so right there is where we're going to see the trip point. So then so I'm going to take that to being good. And then I want to coordinate it with my my CT with a relay R16. So let's pick up R16. Now I'm doing this piecemeal just to keep from being confused. And the idea is when I get it all put together, we should be able to coordinate it. So again, single ground, single phase, fault the bus. And what we see on our Westinghouse is I've got some settings in there. Again, this is going to be the same. This is just a 51G. All right, here I've got the correct CT set up, but I don't have the correct device function. So I need to pick out 51G. I need to pick out the breaker that I'm going to be operating, just staying with my convention of the BH2. And then go into settings. And again, we're looking for I want to be up close to 380 amps. So. All right, and it's set to trip at a definite time on the dial of ½ a second. So we can apply these. Let's see how it looks on the fault. It's not showing me anything. What's going on? All right, so here's our 16 set point. And still have a couple. I think I closed the box without saving it. Again, typical errors when you're looking at the let's see, so 400 amps, ½ a second, no instantaneous. And let's look at how thick the line is. Let's give it a little bit more weight. All right, so it's chopping off my plot. So let's try include a downstream load or downstream device. It should get us there. Now, as I mentioned, this is a little tricky in terms of trying to do this live, because sometimes you need to take a little bit more time looking for the specifics. But if we fault all the buses, we get our 300 amp. I'm still not seeing my relay. All right, this may be point where I have to take it offline and think it through, but let's try looking at it one more time. Ground over current. Momentary clipping. Let's don't clip anything. Let's look for function 1 to 500. Okay, there it is. So the clipping got me. This is showing that it's going to be picking up right at 524, so I missed the boat. Now it's picking up at 461. So again, the clipping is probably the second or third most common mistake, and you just watch me muddle through it. And so this gives us a possibility, now if I'm happy with that particular setting, of going back and closing this. And then if you will bear with me, here's where the TCC that was saved with the file. So this is where we're attempting to end up as the result of coordination. So again, so we want to look at the ground fault, single bus, single phase, fault all the buses. Now we're showing the downstream relays. Here's R7 and R6, which will be the first ones that are tripping. R6 here, and R7 here. And then as we fault individual buses with no clipping, we see we have the upstream breakers as backup for the downstream faults. Okay, that was a little clumsy. I apologize. It does take some time and effort to understand exactly what you're looking at. There is, in this particular example, a good discussion or presentation on coordination from breakers. You can coordinate against the breakers with the TCC curve in panels and motor control centers, and feeder breakers both inside the motor control center and the mains upside. And so for those kind of coordinations, I think we even have a plot. And so here we're showing relays upstream. This is more relays. I believe we have one here with the breakers. Yeah. So this is showing the breakers and the fuses, and it's just run out of time. I encourage you to walk through the example where we're looking at the ground fault, single phase, fault that particular bus, and how it measures up against the settings for ground fault. In fact, I think on this one, yeah, this one is has problems too. So this would be worth walking through. For instance, the fuse is the only thing it's showing, and it's possible to have coordination with the feeder breakers and main breakers in a panel. Oh, sorry for kind of stomping all over that. If you've got specific questions, by all means, send me an email or enter in the chat for this webinar. And if you're struggling with coordination in your own system, by all means, feel free to contact tech support via email or phone. We still are doing online regional training, and we're trying to schedule live training here towards the end of the year. Keep an eye on the newsletter. Check out the website, and and the website banner on the tool start page. Thank you for joining today. And like I say, I'll check out the questions and see if we can answer them via email. Have a good day.